Hello, this is the next video in a playlist that I'm calling General Linear Models Design of Experiments, and this is part 5 of an 8-part little mini-series within that playlist. Here we're looking at contrast in the balanced two-factor factorial design with interaction. Now, as a reminder, the model is this, so it's x star beta star plus epsilon, equal to y. So it is a linear model, but then we partition this x into a constant term, part associated with factor A, factor B, and the interaction space plus air. And I'm going to point you back to parts 1, 2, and 3 for more detail on the model. So contrast in the alphas or betas equivalently. But we'll just do it for alphas, and it also applies for the betas. So we're going to show that contrast in the alphas are hard to interpret and probably should be avoided. So Theorem 1 says that if this term, lambda transpose beta star, is estimable, such that, when you do the product, it's actually a linear combination of the alphas, such that, so it's the sum from I equals 1 to A Ci alpha I, where the Ci is summed to 0, and the lambda here is part of the row space of the design matrix, so row transpose x star, then row transpose times m, the perpendicular projection matrix on the column space of x star, is equal to this. So it's row transpose times m alpha minus j. M alpha is the perpendicular projection matrix onto the column space of x alpha, and this is the perpendicular projection matrix onto the column space of 1s. So the proof goes like this, that lambda transpose can be thought of as this. So, this is associated with mu, these are the beta parameters, and these are the interaction terms. So we only want the linear combination of the alphas, so that's why this is called C. And since lambda has to be a part of the row space, this has to equal row transpose star. Now remember, we're assuming that it is estimable, which means that lambda has to be a part of the row space. So for some row, this is true. So now x star can be partitioned into this factorial design with interaction, and then we take row times each of those, right? But row times 1 has to be 0. This has to equal C. That's 0. That's 0. So this implies that row is actually orthogonal to this column space, 1 x beta and x alpha beta, right? But this column space is actually equal to the column space of the interaction space, but which that is also equal to the column space of the perpendicular projection matrix onto that column space, so m alpha beta. Now notice that m alpha beta minus this is a perpendicular projection matrix onto the orthogonal complement space of this, right? Because this matrix, if it's m alpha plus m beta minus j, is the perpendicular projection matrix onto this. This is the perpendicular projection matrix onto this column space. So if you take the difference, and this is a subset of that, so that difference is another perpendicular projection matrix onto the orthogonal complement space of this with respect to the column space of x alpha beta. So if we, therefore, if we take this multiplication, row star times this, right, which is this right here, then we get this, right? Because those are orthogonal. And so we get this times this, right? So if we multiply that in and then take this piece to the other side, which this implies that row transpose m, and m and m alpha beta are equal, it's the same perpendicular projection matrix, is equal to this, right? Based on that. And that's what we wanted to show. But now, what's the consequence of Theorem 1? So lambda transpose beta star is equal to this, right? It's estimable, so that lambda has to be part of the row space. And now we can put an m here because this is the perpendicular projection matrix onto x star. So mx star is just x star. But this, according to Theorem 1, and we're assuming that we have this set up here, that it's a treatment contrast, is equal to this. Okay? But this is not a linear combination of the alphas. So from part 3, we showed this. So lambda transpose beta star, which is equal to this. If we look at just this x star beta star, it's this right here. Right? So each row of this setup, so each row of this is, you know, it's an alpha I, right? Plus, or, you know, minus a constant, plus one of these terms, minus this constant. So since these are constants, they're not indexed. So thus this linear combination of the betas is actually a linear the beta star, the parameters, is actually a linear combination of alpha I and that interaction term I, star. And so we're not taking a linear combination of the alphas. It's really a linear combination of the alphas and the interaction terms, which is not what we intended it to do. So similarly, in the betas, if a contrast in the beta is really a contrast in these terms here, which is really not the intended purpose of trying to calculate a treatment contrast. So note, we must focus linear combinations in the interaction terms. So a contrast in the interaction terms is this. So it's gamma, which is equal to the double sum over all the, it's a linear combination of all the interaction terms. The constants out here, for every j, if we sum over I, it's 0, and then for all I, if we sum over j, it's 0. Alternatively, in matrix form, we can write it like this, where lambda is this. So we have all 0, so we're not picking off any of those, and we're only dealing with the interaction terms. And that's actually how you do contrast in the two-factor factorial design with interaction. Now granted, this has to sum to 0, right? Those have to add to 0. So, and we will look at this in our art illustration, the last video of this little mini series. So last theorem, and we're only going to heuristically show this. So an orthogonal set of a minus 1 times b minus 1 contrast partitions the sum of squares for the interaction space. So the proof, this follows almost identical to part 6 of the previous mini-series on factorial design without interaction. So we will give an outline here. So one is we want to show that this vector, right, this is a matrix times a vector, which creates a vector, is part of this column space. So this says it lives in the column space, the interaction column space, but it's orthogonal to the previous parts. So in regards to factor A, factor B, and the constant. So 2, we want to show that if we create these orthogonal contrasts, then they form a basis for this column space. The normalized vectors in 2, so each of these, can be used to create a perpendicular projection matrix onto this column space. And then we use these vectors to partition the sum of squares associated with alpha beta. And I did that pretty fast, and really, if you haven't watched the previous mini-series, specifically part 6, this may be a little vague, but in the interest of the time, I just wanted to keep it that way. So I hope you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.